All right, so get this. We're diving into a research paper that claims it's cracked the code on accelerated learning, not just for AI, but maybe even for us.
And it's not just hype. The paper Iterate to Accelerate lays out this really compelling mathematical framework for how iterative reasoning can supercharge problem solving.
Okay, iterative reasoning for, those of us who haven't been studying algorithms all week. What's the quick explanation?
So think of it like this. Instead of trying to solve a problem in one giant leap, you break it down into smaller steps and you keep refining your approach based on feedback.
So like editing a draft of a paper, you don't just nail it on the first try, right? You got to have those revisions and keep building on each draft till you hit that sweet spot.
Exactly. But what's really cool is that the paper goes beyond just, showing the benefits of iterative reasoning. It actually dives into the math and proves how, under the right conditions, this approach can converge to a solution much faster than traditional methods.
Oh, okay. So we're not just talking about marginally faster. We're talking about a whole different order of magnitude, right?
Absolutely. They've shown that their proposed iterative scheme achieves a convergence rate of 1 over c squared, where c is the iteration number.
1 over c squared.
Yeah, this means the error shrinks proportionally to the inverse square of the number of iterations. Basically, it finds the solution much faster than the usual 1 over c rate.
Wow. So what's the secret? What makes their approach so much faster?
This is where it gets a bit technical, but bear with me. The key is a cleverly chosen averaging parameter,
Okay.
specifically 2 over the quantity c plus 2.
2 over c plus 2.
Yeah, this parameter acts like a fine-tuning mechanism, making sure each step in the process is as efficient as possible.
So it's like finding the perfect balance between taking those bold leaps forward and making, subtle adjustments as you go.
Yeah, that's a good way to put it. Now, are you ready to venture into some less familiar territory?
I think so.
Because at the heart of this whole framework is something called Bregman divergence.
Bregman divergence. All right, the inevitable foray into the more technical side of things.
Yeah.
But before you unleash all the mathematical jargon, give me the layman's version.
Sure.
What is Bregman divergence and why should I care?
Okay, so it's less about memorizing a formula and more about understanding its role. Imagine you're trying to navigate this complex landscape, but instead of mountains and valleys, you're dealing with these abstract mathematical spaces.
I see.
Bregman divergence is like a compass in this terrain, helping you understand the relationships and distances in these non-Euclidean spaces.
Okay, so why are these non-Euclidean spaces so important?
Well, because the real world, especially when we're talking about, complex systems or AI, it rarely behaves in a nice, neat and tidy way.
Right.
Many problems, especially in AI research, they operate in these more abstract spaces.
So Bregman divergence is like our tool for navigating the twists and turns of these, complex landscapes. It helps us find the optimal path, even when it's not a straight line.
Exactly. And this is where another piece of the puzzle comes in, mirror descent.
Okay, here we go. Another technical term. Hit me with it. What is mirror descent, and how does it fit into all of this?
Think of it as gradient descent, but with a twist. It uses Bregman divergence to efficiently navigate those complex non-Euclidean spaces we were talking about.
Right.
It's essentially a way to find the optimal solution, even when the problem space isn't behaving in a predictable Euclidean manner.
All right. So we've got iterative reasoning, we've got Bregman divergence, and now we've got mirror descent. Feels like we're building up to something big here.
We are, and the next piece might surprise you because it's a concept you might already be familiar with, dynamic programming.
Wait, dynamic programming? Isn't that like a classic computer science technique?
Yeah.
What does that have to do with all this cutting edge AI stuff?
That's the beauty of this paper. It connects seemingly different fields.
Okay.
Remember how dynamic programming is all about breaking down a problem into smaller, more manageable subproblems? Well, that's another form of iterative reasoning.
So it's like they're both sides of the same coin, just applied in different contexts?
Exactly. And the paper's framework actually captures both mirror descent and dynamic programming, showing how they're similar and how they both contribute to accelerated problem solving.
Okay, my mind is officially blown, so we've established that iterative reasoning is this, powerful tool, but where does AI fit into all of this, specifically those large language models everyone's talking about?
Ah, that's where things get really interesting. The paper points to chain of thought prompting as a prime example of iterative reasoning at work in LLMs.
LLMs?
Yeah, these models don't just, magically produce answers. They actually think step by step and refine their responses with each iteration, much like the iterative framework we've been talking about.
So instead of just spitting out a final answer, They're showing their work, letting us peek into their thought process as they refine their understanding.
Exactly. And this isn't just for show. This iterative approach is crucial for LLMs to achieve, more accurate and complex reasoning.
So, like the difference between a student who just memorizes the answer and one who actually understands the concepts
Right.
and could apply them
Yeah,
to new situations.
exactly.
This is all incredibly fascinating, but I can't help but wonder, what's the catch? There has to be a downside to all this, right? I mean, iterative reasoning is so.
Oh, hey, I think our listeners got to say.
Hey there. So, what's the RNN recurrent network in the role for this paper?
That's a fantastic question, and it really gets to the heart of the paper's argument.
Yeah, I'm curious too. I mean, we talked about feedback loops, but how does this tie into recurrent neural networks specifically?
So the paper doesn't explicitly use the term RN or recurrent network as an implementation, but it heavily implies them with the ideas of iterative reasoning and feedback loops.
Okay, so it's more like the paper lays the theoretical groundwork for why recurrent networks are so effective.
Exactly. The core idea is that recurrent networks, by their very nature, embody this iterative feedback. They take previous steps in the process as an input for the next step.
So it's not just about processing information in one go. It's about going through multiple iterations, kind of like the way we think, constantly refining our understanding.
Precisely. And the paper's depth separation result highlights that recurrent network architectures are more efficient for approximating complex functions than feed-forward networks that don't use feedback.
So you need exponentially larger feed-forward networks to get the same performance that a recurrent network could achieve using feedback.
Exactly. The paper gives a mathematical reason for why feedback is necessary for certain types of complex tasks, and recurrent nets naturally employ feedback mechanisms.
So they are the natural choice in these iterative frameworks, and it looks like this paper is putting a mathematical basis for that choice.
Right, and that's why it's so exciting, because it gives us a deeper theoretical understanding of why recurrent networks are working so well for these applications.
Okay, that makes a lot of sense.
Oh, go for it.
So, can we explain the update rule in this paper?
Absolutely, that's a great question. It's key to understanding the entire framework.
Yeah, I'm curious too. We've talked about iterations, but what's actually getting updated?
So the paper introduces a generalized update scheme, and it's really what makes the whole thing tick.
Okay, unpack that for me. What does the update scheme look like?
Well, it's a mathematical equation, but let's try to break it down. The core idea is that with each iteration, we're refining the current state by using an update operator.
Okay, so this update operator is what actually changes the state each time.
Exactly. And this update operator takes two things into account, the current state and some auxiliary information.
So it's not just changing the state randomly, it's incorporating some additional information.
Right. And it also includes this term for perturbations, which we'll talk more about later. This helps account for real-world noise.
So the update operator is kind of like the engine of the iterative process, fine-tuning the model with each step.
Yes, but it's designed so that each step brings you closer to the solution. This is where the Bregman divergence comes in.
Got it. It's like navigating towards a goal in those non-Euclidean spaces we talked about.
Precisely. And this framework really unifies a lot of different methods, so it can describe mirror descent and dynamic programming, which we've talked about.
Okay, so the update mechanism is flexible enough to encompass these different approaches.
Yeah. And that flexibility is crucial because it allows us to apply this framework to all sorts of different problems.
That makes a lot of sense. Thanks for clarifying. But as we were saying before, if this iterative reasoning is so powerful, why isn't everyone already using it?
That's a great question, and one that we'll delve into now. While iterative reasoning has enormous potential, it also comes with its own set of, challenges and limitations.
Okay, you've officially piqued my curiosity. I can't wait to hear more about these challenges and how researchers are tackling them.
Yeah, and that's what we'll be talking about now. It's time to explore the other side of the coin and uncover the complexities of iterative reasoning.
Right, because it almost sounds too good to be true.
Yeah.
If iterative reasoning can accelerate learning and problem solving, why isn't it being used everywhere?
That's a good question. And the answer, well, lies in understanding that iterative reasoning isn't a magic bullet. It has challenges and limitations. One of the biggest hurdles is dealing with noise.
Noise. Like literal background noise, or is this something else?
Not literal noise, although that can be a factor. What I mean is the inherent uncertainty and messiness of real-world data. Data is wildly perfect.
Right.
There are always gaps, errors, and inconsistencies.
So it's like trying to solve a puzzle where some pieces are missing or don't quite fit.
Exactly. And for iterative processes, this noise can be a real stumbling block.
I see.
If the feedback you're getting is unreliable, it can, throw off the entire process.
That makes sense. Like trying to navigate a maze with a broken compass, you might end up going in circles.
Exactly. And this is where the robustness of the iterative scheme comes into play. The paper really emphasizes the need for algorithms that can handle noise, filter out the irrelevant information, and focus on the signals that matter.
So it's not just about speed, it's about being reliable even when things get tough.
Right.
But how do you design an algorithm that can tell the difference between signal and noise?
It's definitely a challenge, but there are a few strategies researchers are exploring. One is to use statistical methods that can identify and downweight noisy data points, so you're giving more weight to the more reliable information.
So it's like a built-in noise filter
Yeah, exactly.
that helps the algorithm focus on the good data.
Right. Another approach is to use techniques from robust statistics, which are designed to be less sensitive to outliers and errors in the data.
Okay, so dealing with noise is one challenge. What are some other limitations of iterative reasoning?
Another big challenge, especially in AI, is the computational cost of iterative processes.
Okay.
Each iteration takes time and resources. And for complex problems, the number of iterations needed to get a good solution can be, quite a lot.
So even though each step is making progress, the whole process can still take a long time and a lot of computing power.
Yes, especially as we develop, more and more sophisticated AI systems. Yep, go on.
What's the difference between the delta rule and this paper I mentioned update schema?
That's a really interesting question, and it touches on some key differences between classic learning algorithms and this more modern framework.
Yeah, the delta rule is a really foundational concept, and seeing how it fits into this iterative picture is insightful.
Okay, so for those who might not be familiar with the delta rule, it's a learning algorithm that's typically used in neural networks, right?
That's right. It's all about adjusting the weights of connections based on the error between predicted and actual outputs. The adjustments are proportional to this error.
So it's like if a neuron makes a mistake, the connection that caused it is punished, while connections that did good are rewarded.
Exactly. And it's a key ingredient for how neural networks learn, a simple yet powerful method of getting closer to the desired behavior.
But as I understand it, it's often just a single update step, right? You calculate the error and adjust the weights, and that's that.
Yes, here the key distinction lies in how this paper approaches learning. It's not just a single error correction, but a more general iterative scheme, as we were talking about.
So it's not just a single step, but many of these steps, and each step is based on a more complex process that we were discussing earlier.
Precisely, the iterative framework in the paper uses this generalized update operator that incorporates not just the error, but also auxiliary information and even noise.
Okay, so it's like the delta rule has a similar objective, but the update operator is more advanced, it's more nuanced, and takes more variables into account.
That's a great way to put it. And this paper scheme, as we've discussed, is based on Bregman divergences, non-Euclidean geometry, which can capture, more complex relationships in the data.
So it's not just about correcting errors, but also about learning from the structure of the data in the best possible way.
Exactly. Also, remember how we're talking about the accelerated convergence? Well, the delta rule doesn't always have these types of convergence guarantees. This generalized scheme can actually prove convergence.
So it's not just adjusting parameters, it's adjusting them in a way that provably leads you to a solution faster and in a more robust way, a way that takes into account some other variables.
Yes. The delta rule is also typically used in the forward pass of a neural network, not in feedback loops. This framework we're discussing highlights the advantages of those loops.
That's a good point. It's not just about updating parameters, but also about learning by using these feedback loops, which are so crucial to this framework.
Yeah, so while the delta rule is a cornerstone of many algorithms, this paper's framework presents a broader perspective on iterative learning.
Okay, that makes a lot of sense. So thanks for clarifying the differences. But as we were saying before, if this iterative reasoning is so powerful, why isn't everyone already using it?
That's a great question, and one that we'll delve into now. While iterative reasoning has enormous potential, it also comes with its own set of, challenges and limitations.
Okay, you've officially piqued my curiosity. I can't wait to hear more about these challenges.
Oh, yeah, uh-huh.
It's not true. You can do a reflection.
Oh, yeah, let's hear it.
Hey, can you do a reflection of this podcast? and wrap up the conclusion.
That's a great idea. I think reflecting on what we've discussed could really help to bring everything together.
Yeah, a little recap to tie it all up sounds perfect.
So to start, we've explored how this paper offers a unified framework for iterative reasoning.
Right. It's not just about one specific method, but rather a whole perspective.
Exactly. And that framework connects classical optimization techniques with modern AI methods.
Like from mirror descent all the way to those large language models.
And at the core of this framework is the idea of iterative updates that use feedback.
Yeah, it's all about these loops of refining the solution with each iteration.
And we've seen how Bregman divergence and a carefully chosen update parameter are key to faster convergence.
Right. It's not just any updates, but updates that consider non-Euclidean geometries.
And it's not just speed, it's also about robustness in the presence of noise.
Exactly. If your feedback is noisy, you need to be able to filter that out and focus on the good signals.
And we've touched on the idea of recurrent networks as a natural way to use feedback, even though it isn't explicitly in the paper.
Yeah, it's a natural fit for that iterative approach with their built-in feedback loops.
So while iterative reasoning is really powerful, it isn't without its challenges.
Right, like the computational cost and dealing with the messiness of real-world data.
And we were talking about the delta rule and how it relates to the update. They do similar things, but in different ways, in different contexts.
Right, the update in the paper's framework is more generalized and has theoretical guarantees.
So it's clear that while iterative reasoning has huge potential, it also requires careful consideration of the challenges.
And this paper lays some really key groundwork, really good insights into understanding that power of iteration.
Yes, it's showing the potential of combining techniques to produce more powerful algorithms.
And I think our conversation really helped drive that point home. So thanks for joining us on this journey.
Yes, it's been fascinating, and I hope that you found it helpful.
And as always, we really appreciate you joining us. It's time to sign off now.
Yes. We hope to see you next time for another deep dive.